Hello all, welcome to the EduMoon tutorials. In this series of videos, we are discussing about formal language and automata theory. So today in this video, we'll discuss about context-free grammar, which is also called as CFG in short form. So this is a type 2 grammar, which we earlier discussed in Chomsky hierarchy in the first video of this playlist. So CFG is the production rules in CFG grammar are like alpha tends to beta. So every production is in terms of alpha tends to beta, where this alpha belongs to capital V, that is variable, and beta belongs to V union T whole star, that is any number of combination of variables and terminals. So here we can see that alpha is always belongs to V, that is only a single variable on the left hand side of the production rule, and the right hand side we can have any number of variables and terminals. So let us take an example here for a grammar which is generating a language. So let us take a language L is equal to 0 power n and 1 power n. So this is a language familiar where we solve this problem using pushdown automata in the earlier videos. So language L equal to 0 power n 1 power n, that is the strings that are generated in this language where n is greater than or equal to 0. So if you write this set of strings that are generated here, since n is greater than or equal to 0, when we put n equal to 0, it is an empty string, so we write epsilon here. If n equal to 1, it is 0 1. And if it is n equal to 2, it will be 0 0 1 1. Next 0 0 0 1 1 1, and so on. The strings are followed that language. So this is the language. If we take this as a language, the grammar that generates this language is context free grammar. So the grammar is given as s equal to, when s tends to 0, s1 or epsilon. So this is the language that is going to generate the strings in the above language. So let us take for example a string here, that is 0 0 0 1 1 1. So we can produce that string in this grammar by following this one. So first we take 0 s1. Again this s can be written as 0 s1 using the same production rule. So that becomes 0 0 s1 and 1. So again this s again replaced with the same production rule, that is 0 0. Again this s turns to 0 s1. The remaining two ones are there. So finally this s can be stopped using that epsilon production. So finally it becomes 0 0 0 1 1 1, which is the string that is available here. So likewise any number of strings can be generated using this grammar rule. So this is the grammar rule that is produced in the language L. So this is how we generate the string from the given grammar. So this is what we call as a parsing technique. So there are two types of parsing techniques here we discuss. The first one is top down, the next one is bottom up. So top down and bottom up parsing techniques. So the grammar what you have just seen, that is the string that is generated using the grammar. So we started with the starting symbol s and we came on to the string. So this is called as top down approach. And if it is a bottom up approach, generally we start with the string like this. So we can write the string as 0 0 0 epsilon 1 1 1, because epsilon is an empty string. So I can replace this epsilon as s using this production rule here, s tends to epsilon. So I can write it as 0 0 0 s1 1 1. Now this 0 s1 can again be replaced as s using this production rule. So this will be now 0 0 s1 1, and now again this 0 s1 can be replaced using the same production rule, that is 0 s1. So finally this becomes s again. So here we started from the string here and we ended up to the starting symbol. So this is called as bottom up parsing, because when you write a parse tree, so parse tree is nothing but you can see here, we start with the symbol s and we can write it as a tree structure, hierarchical structure. So initially we have taken as 0 s and 1, and again this is taken as 0 s and 1, and finally again this is 0 s and 1, and this is stop using the epsilon production. So you can see the string and the availability of string like 0 0 0 and 1 1 1. this direction. So this is called as parse tree. There are two types of parsings here. So this is about the parsing tree. So next we discuss about the derivations. So here let us take one more example of a grammar. So let this grammar be starts with the symbol E, which is the starting symbol. E tends to E plus E or E star E or ID, which is nothing but an identifier in a language. So this is very much used in the generating the arithmetic expression in your programming languages, something like A star B plus C and all. So if I want to generate A star B plus C, so all these ABC are the variables or as the identifiers. So simply we write in this grammar, this is an identifier, which is an end string or else the end terminal. So here, what are the variables in this grammar are E is a variable and plus star and ID are the terminals. So now in this string, if I want to generate a string called ID star ID plus ID. So assume this is a string we are going to generate in this grammar. So to derive the string, there are two methods here. So one is what we call is RMD and LMD. So first we discuss about what is LMD. LMD is nothing but leftmost derivation. So the name itself suggests that leftmost derivation is when there are more number of variables in the right hand side of the production rule. First we derive the leftmost variable. So like to generate this string now, so here we take the starting symbol E. So E tends to, for example, if I take E star E, right? So there are two variables in the right hand side of the production rule now. So I take the leftmost one first always in this production, this derivation. So this E can be written as ID using this production rule here that is available here. So is ID star E. So next, since there is only one variable here, so I can use this one. So this E can be generated as again E plus E. Now again there are two variables in this one, so I'll take the leftmost variable that is this one. So I can make it as that E as ID again plus E. And finally there is only one variable here, so that is the leftmost one. So I make it as ID. So this is how this string is generated in the grammar. So this is LMD where we always start with the left hand side of the production rule here. So whenever there are two variables, we select the leftmost one. So the second one is nothing but the RMD. So which is nothing but rightmost derivation. So here we start with the rightmost variable. So for example, if I write it as E star E initially, so I can take this one the rightmost variable. So first of all, I'll generate that one. So I'll derive that as E plus E. I can rewrite that E as E plus E using this production rule, the first production rule here. So now again the rightmost one. So this one we generate that one. So we derive that E as ID first. So this E is replaced as ID. So next the rightmost variable is this one. So next we generate E star ID plus ID. And finally this one. So we get ID star ID plus ID. So this is rightmost derivation. So LMD is leftmost derivation and RMD is the rightmost derivation. And we see something called as ambiguous grammar or else ambiguity in the grammar. So this grammar actually is called as ambiguous grammar because we'll generate two parses for the same string. So we see that with an example now, the same example. So when we generate a parse tree for this example, what we have taken here. So initially, if we draw the parse tree here, so E is generated as E star E initially. So write it as E star and E. Next we generated this E as ID here, and next this E is generated as E plus E. So this is E plus E. Then we have this as ID and this one as ID. So this is the parse tree that is generated for this LMD derivation for the string id star id plus id in the given grammar. So similarly, you can also generate another parse tree, the same LMD, where you can start. I can directly write the parse tree here. So for example, if we take initial E as E plus E, so I take the leftmost one again. I generate this one as E star E, and finally this leftmost one as ID, and the next leftmost is this one ID, and finally this one is ID. So in both the cases, you can see that we got a string ID star ID plus ID here, and also this tree ID star ID plus ID. So there are two parses that are generated for the same string in the given grammar using the LMD. Similarly, we get for RMD also. So this grammar is simply called as ambiguous grammar, and this property maybe is called as ambiguity. So we need to check a grammar whether it is ambiguous or not. If there are two parses generated for the same string in the given grammar, then that grammar is called as ambiguous grammar. Next we go with the types of grammars. So types of CFG. So generally there are no much categories in the CFG, but you can see that there are some CFG grammars which are finite, which generate a finite set of strings. Like for example, if you take a grammar s tends to 0, a 1, and a tends to b, and b tends to 0. Now this grammar generates only one set of string. So the number of strings that are generated by this grammar are finite actually. So for example, even if I write is b1 here, so this generates actually only one string, because no variable is deriving the same variable. So the second category you can take it as is infinite, or as the recursive grammars, where if at all the string is generating the previous example like this one, so always the same string, the same variable is generating the same variable again. So it's like a function calling itself in a C programming, which is like recursion. Here the variable is generating the same variable. So these are called as recursive grammars. So the finite grammars are also called as non-recursive here. These are basically non-recursive, and these are recursive grammars. So here again, recursive grammars, because it's called infinite because the set of strings generated are infinite. Like in this grammar, we know the strings are uh, 0, 1, 0, 0, 1, 1, and so on. It gives us infinite strings, right? And in recursive grammars, there is also something called as left recursion, which is very important. We'll be discussing that again in the later classes. What is left recursion means? The grammar is again generating the same grammar, and the variable is in the starting itself, like this one. Okay, on the right hand side of the rule, the first symbol is again the same symbol, so we call it as left recursion. And if at all it is a right recursion, if it is a right recursion, so you can see that s tends to 0, 1, s. So here you can see that this is repeated at the end of the production rule, so that is called right recursion. So this is where we had this is a general recursion statement where the symbol is in the middle. So these are some types of grammars which are generating a finite strings or infinite strings. So in the next video, we'll be following with the other topics of the CFG chapter. So in the next video, we'll be seeing about the simplification of the context-free grammar. So there are some set of rules which should be followed for the simplification, and the normal forms, which are really important in this chapter. Normal forms. There are two normal forms. Those are CNF and GNF. So we'll go with these topics in the next video. Thank you all.